All right, good afternoon, guys. So today we're going to start talking about the next topic in the course, and that topic is functions. So it turns out that functions are essentially just an application of sets, which is what we just finished talking about, which is why we're going to talk about functions next. So a function is just something that maps from one set to another set. Okay, so suppose that you wanted to do that. So suppose we want to map one set to another set. So what does that mean? Well, given an element of one set, let's call it A, or the input, we want to return an element of the other set, let's say B, the output. So given an element of set A, which we call the input, return an element of set B. Which we call the output. That's what we'd like to do. So as an example, you could have the set A be the set of all users on a computer system of some kind. So it's all things X such that X is a user on, I don't know, let's say CUlearn. Okay, that's the input set. And the set B we could define as the set X such that X is a valid password. All right, so CUlearn has all these rules about what counts as a valid password or not, right? It has to have an uppercase character, a lowercase character, and a number, and maybe a symbol or something like that. So you look at the set of all possible valid passwords, and that's the set B. Some of them won't be used by anyone, but they're still valid, so they're still in the set B. So one question you might want to ask yourself is, given a user, what is that user's password? Given a user, what is that user's password? That seems like a natural question to ask. All right, well, in that case, the input is the user. So this is input from set A. And the output of this operation is that user's password. And it's from set B. Right? The inputs are users, so from set A, and the outputs are passwords, which are from set B. All right? This thing that we're describing is all that a function is. That's all there is to a function. So if A and B are any two sets, then a function from A to B is an assignment of exactly one element from B to each element of A. So exactly one element of B, or sorry, from B, I should say, to each element of A. So all that means is no matter what input you give, it produces some output. Right? That doesn't work in the reverse direction, right? There are some passwords that nobody has, but everybody has a password. That's all that is saying. All right, so we have some notation to go along with functions, as you might expect. We write f of A equals B, if B, little b, is the element of big B that gets assigned as the result or the output of the input A. Okay, so if some B in B is the unique element assigned by the function f to the input element A. And the input element is drawn from the set A. All right, and if f is a function from A to B, then we write f is a function from A to B. So f colon A arrow B. That means f is a function and its inputs are drawn from the set A and its outputs are from the set B. That's what it means to be a function. All right? And notice that it makes sense to model the password example above as a function because every person has exactly one password. If you had 2 passwords to CUlearn, that's okay, but then you wouldn't use a function to model it. You use something else called a relation that we'll talk about later. So for now, it's important to understand the limitations of what we're doing. Functions have this thing where the output is a unique single element. If you want to account for the possibility of not having a password or having 2 passwords, that's okay, but you can't do it using functions. Right? Functions don't allow you to do that. All right, so let's see an example. So we have a bunch of users. Let's say the user root has the password 123, as you would want the root user to have. User John has the password, let's say, P455W0RD. Who has that same password on their luggage? And then let's say we also have a user guest. So user guest has password hello. Okay? So we could come up with this function called the password function. And I'll call it P. You can visualize P in a few ways, but before we do that, let's explicitly write down exactly what the function is. The function is this. We have P root equals 123, P John equals P455W0RD, and we have P guest equals hello. So that explicitly states for every input, what's the output? You can define a function like that if you want, but I hope you agree that this would get tedious after a while. So we have other ways to represent functions, and we'll start talking about those as we go along. One way you can represent a function is visually. So we can represent it visually. And the way you do that is this. You have the input set here, let's call it A. The output set here, let's call it B. And then you have the elements of A, so root, John, guest. And then you have the elements of B. So there's a whole bunch of passwords. Some of them are 123. One is P455W0RD. And one of them is hello. But there's lots more valid passwords than just those 3. And the function looks like this. It takes root, the input, to 123 as the output. It takes John, the input, to P455W0RD as the output. And it takes guest as input to hello as the output. All right, so this is how you, one way to represent a function visually is to draw a diagram. And these arrows here, these blue arrows, those really define what the function does. Yeah?
Isn't it okay in a function if two inputs produce the same output?
Yeah, that's totally fine. So two people could have the same password. There's a special term for that that we'll get to later, but it's allowable by the definition of a function, yeah. Yeah. Other questions? Yeah?
If like someone doesn't have passwords, could we not say no or something? Or is that not?
Right, so at that point, you would sort of increase your possible output set. And if that's a reasonable choice in whatever you're trying to model, then yeah, you can do that. In this example, I would say that's probably not usable on the part of, say, CUlearn, because then what do you do for that user?
But like, if there's like a computer account you have, and if a guest account and you have to usually a guest account.
Sure, so if you wanted to model that, you can do it that way, but then null, the special password, would have to be part of the set B. So you need to take that into account. And then whatever representation you use for that couldn't be someone else's password, or if it is, then you would have to handle that as well. Other questions? All right, so let's do another example. So consider the function, I'll call it G, that assigns a grade to each student in this class. All right, so there's lots of different ways you could represent this. Let's represent it visually, because that's what we're learning. So we have this set on the left, and this is our set of inputs. And really, this is the set of students in this class. So I'm going to simplify it a little bit, and rather than write out 370 things, I'm just going to write Tim, Joe, Lee, Tom, and Mark. All right, and now we have this set of possible grades. And again, I'm going to simplify this a little bit and just say the possible grades are A, B, C, D, and F. All right, I'm not going to include the pluses and minuses. You could if you want. I just don't want to make the example too big. All right, so now let's look at what the function is. So let's say that Tim gets an A, Joe gets an A, Lee gets a B, Tom gets a D, and Mark gets a C. So happily, no one fails. That historically does not actually happen in this class. Okay, so a couple of things. There's two interesting things about this function. The first is that nobody failed. So F is actually never an output of this function. But it's still considered to be in this grade set. We'll talk about that distinction later on. The other thing you might notice is that two people got the grade of A. So the output A was produced by more than one input. In this case, two inputs, but in general it could be any number of inputs. Well, any positive number of inputs. Okay? So those are interesting things about functions. This idea of, given an output, how many times does it appear? Right? We know every input has exactly one output, but if you look at the outputs, how many inputs do they correspond to? That's an interesting question. We'll talk about that a lot. All right, so functions can be specified in several ways. So the first one is the first one we saw, and that is to explicitly write out each pair. And that's, as you can imagine, a lot of work. So an example would be like p root equals 1, 2, 3, and so on. You generally don't want to do that because it takes forever. Another way of specifying a function is with a diagram, like we did above. The problem with that is, again, it sort of takes a while, and if you'll remember from when we were talking about sets, there are sets that are infinite. So it's going to be very hard to draw an infinitely large diagram. So to get away from that, we go to the idea of expressing a function as a formula. And this is something people have probably already seen. So I could give you a function like f of x equals 2x squared plus 1. Right? And it's clear what's happening here. If you give it an input x, the output is you take x, you square it, you double it, and then you add 1. Right? That's describing how the function works instead of explicitly giving every input and output pair. And this is nice because now you've expressed a lot of input and output pairs very succinctly. Right? If x could be any integer, then I've expressed a function that has infinitely many inputs in almost no space, which is nice. All right, and then the last way to really specify a function is with a program or an algorithm, if you like. And we don't really talk about that in this course so much. We'll cover it a little bit, but mostly that gets deferred until subsequent courses. The idea is if you want to describe a function, one way to do it is to write a program that computes the function, and whatever input you give the program, well, whatever output that produces is the value that corresponds to it. So you put input into program, and the output is whatever the program gives you. All right, that's another way to specify how to define these things. We don't talk about that so much in this course, but you'll see it later. All right, so now that we know how to specify functions, let's start talking a little bit more about them. There's lots of terminology that goes along with functions. So let's say we have a function. Let's say it's the function f, and it goes from the set A to the set B. We have special names for A and B. So A is called the domain. So the input set is called the domain. The output set, B, is called the codomain. So if you look at the definition of the function, the domain is the thing on the left of the arrow, the codomain is the thing on the right of the arrow. All right? All right, so now let's say that you knew that f of A was equal to B. All right, so in this case, A is called the image, A is called the pre-image of B. Pre-image of B. And on the other side, B is called the image of A. Is that okay? All right, so now if you go through the function and look at the set of all possible images, that set is called the range. So in the past, depending on how things went for you in high school, you might have heard of the domain and the range of a function, and usually we ignore talking about the codomain. So the range of a function is the set of outputs you actually get, and the codomain is the set of outputs that are possible. So if you look at this in terms of the password example, so the function that maps usernames to passwords, the codomain is the set of all valid passwords, but the range is the set of passwords that people actually have, right? Because there's lots more passwords that are valid than people actually have. Is that distinction clear? Because that trips up a lot of people, and it's important to understand that. Okay. So let's do some more stuff. If we go back up to the example we had before, so I'll just draw it again down here. So we have this set of students, and it consists of Tim, Joe, Lee, Tom, and Mark. And we have this set of grades, and it consists of A, B, C, D, and F. And the function looked like this. Tim had an A, Joe had an A, Lee had a B, Tom had a D, and Mark had a C. So let's try to figure out what the, and this function is called G. So let's try to figure out what these things are. The domain is the set of all possible inputs. The inputs are the students, so the domain is Tim, Joe, Lee, Tom, and Mark. That's what the domain is. The codomain, well, that's the set of all possible outputs. So that's A, B, C, D, and F. The range is the set of all actual outputs. And notice that nobody got an F. So it's A, B, C, D. And that shows you that the range and the codomain are different here. They might not always be different, but they can be different. Okay, they don't have to be different, but they can be. All right, so we also have these image and pre-image. So we know that F of Tim equals A. So what that means is A is the pre-image of Tim. Or sorry, the image of Tim. Okay. And conversely, Tim is the pre-image of A. Is that last sentence, Tim is the pre-image of A, is that a good way of phrasing that? Yeah? Yeah, I would better phrase this as Tim is a pre-image of A, because you say Tim is the pre-image of A, it makes it sound like there's only one. So really, I would phrase that as A. Do I have to do the same operation in the previous one? Should I say A is a image of Tim or an image of Tim? Yeah?
No, it's the image because Tim only corresponds.
Exactly. Tim only has one grade, therefore it's the image. There can only be one image. Okay? All right. So let's see what happens in a slightly different example. This one I'll define by a formula. So let's say we have this function that goes from the integers to the integers. And it's defined by f of x equals x squared. So what's the domain of this function? Well, the domain is the thing on the left of the arrow. So the domain is the set of integers. What's the codomain of this function? Also z, because the codomain is the thing on the right of the arrow, and the thing on the right of the arrow is z. What about the range? Almost. Not quite all positive integers. They have to be outputs of the function, so it's the intersection of the things you just said. Almost, and 0. So it's the set of non-negative perfect squares. So it's x such that x is a non-negative perfect square. That's the range. Sometimes people confuse range and codomain. Some textbooks don't make this distinction for whatever reason. And some high school curricula don't make this distinction for whatever reason. Range and codomain are different because sometimes we want to talk about one instead of the other. Okay? The thing you can remember is that domain and codomain are easy to determine because you just look at the arrow. Right? Domain's on the left, codomain's on the right. Range is sometimes a little bit more work to determine because you have to actually look at what the function is doing. Okay? All right. So, you can also look at the image of a subset of the domain. So if S is a subset of the domain, you can also look at its image. And its image is the subset of the codomain that consists of the images of the elements in S. Oops. Codomain that consists of the images of the elements of S. And usually we write it this way. We say f of S, which seems weird, right? This is technically not good notation because it only makes sense to stick in elements of the domain. But we just use this notation because you get used to it after a while, I guess. So the image of S is the set of all images of elements of S. So as an example, in the grades example above, if I looked at the image of Tim, Joe, and Lee, well, Tim got an A, Joe got an A, Lee got a B, so the possible outputs for that subset are just A and B. All right, so that's how you look at the image of a subset of the domain. And this notation here is technically wrong, but everyone knows what you mean when you say it. Any questions about any of this stuff? So what we've covered so far is the definition of a function, how to express a function, codomain, domain, range, and image and preimage. These are the important terms that we need to know before we can start talking about the rest of functions. Yeah? Yeah, so this is like saying if you took a group of students, what are the grades possible in that group? So it's almost like you're restricting the domain a little bit. What's the restricted range of that? Right, because this doesn't include the students who got C or D. Because I'm only looking at Tim, Joe, and Lee. So if I look at a subset of the domain, what subset of the codomain do I get? So that's really a subset of the range as well, because the range is a subset of the codomain. All right, other questions? Yes? This thing right here? You would say that it's the image of this set, Tim, Joe, and Lee. But by definition, it has to be a subset of the range. And since the range is a subset of the codomain, it's also a subset of the codomain. Other questions? Yeah?
I just don't understand why the last notation is wrong.
Oh, so you can almost think of it as a type error, right? You have this function f, and it's expecting elements of A, but you gave it a subset of A. So because we've defined what that means, it's no longer wrong. It just kind of looks funny. Okay? Yep. So what would that mean? So there's probably a term to that effect, but I don't know its definition off the top of my head. It wouldn't surprise me if it existed, though. Other questions? All right. So now that we've defined what functions are and some terms for them, we're ready to start talking about their properties. So the properties I want to talk about are injectivity, surjectivity, and bijectivity. So these are properties that functions can have. And this gets back to the earlier observation we made, and that was we had this grades function, and we noticed two people got an A, and nobody got an F. So that's really what this leads towards. There's two ideas of properties there. There's the fact that one output is the result of two inputs. That means something special. And there's also the fact that there's this one output that nothing led to. That is also another thing that's interesting. So let's focus on the first one. So in the grades example, A had two elements mapped to it. So A was the output for two inputs. Similarly, or conversely, I guess you could say, F had none. So these are special situations that we'd like to use to classify functions. We can classify functions based on these situations. All right, so the first situation I want to talk about is this. A function f is said to be injective, so injective, and this is also known as one-to-one. I'll use injective in this course, but you might also see this referred to as one-to-one. If the following thing is true, fx equals fy implies x equals y. So notice this is a statement about logic, so it's a good thing we spent a couple weeks studying logic, or we wouldn't know what this meant. This says whenever the outputs are the same, the inputs are also the same. Okay, so this means you wouldn't have a situation like in the grades example where two different people got the same letter grade. Right? Because in that case, you would have f of, I don't know who it was, Tom, f of Tim equals f of Joe. Right? You'd have f Tim equals f Joe. Guess there wasn't an E. Implies that Tim equals Joe. Well, this is A equals A implies that Tim equals Joe. That's true, that's false. So this whole thing is false. So that means that grades function is not injective. It's not one-to-one. That's the same thing. Okay? I didn't say it, but this is a universal quantification. So if for any x and y, or I guess to be completely clear, I should say for all x and y. Okay? Just so we don't get confused, I'm going to remove this example here. Or I'm going to try to if my stylus cooperates, which it won't. I just don't want to jumble up the definition, that's why I'm taking it out. All right, so that's what it means to be injective. So the function is said to be an injection. So a function that is injective, you would call an injection. All right, so what the kinds of questions you'll see is, here's a function, prove that it's injective. or here's a function, prove that it's not injective, right? That's what you'll see. So to do that, you could prove that this implication is true. You might also remember that because of contraposition, we can write this in the other way. F of x equals f of y implies x equals y is the same as x does not equal y implies f of x does not equal f of y. Right, that's exactly the same because it's the contrapositive. So basically what this means is that each element of the range has exactly one preimage. That's really what this is saying. Each element of the range has exactly one preimage. Right? So I mean, really what it's saying is that it has at most one preimage, but we already know that it has at least one. So it has exactly one preimage. Or maybe we don't know that, and we'll find out in a second. One of them. All right, so is this clear? Each element of the range has exactly one preimage. Is it clear what that's saying? So it's the opposite of the grades example. In the grades example, this element A, so up here, this element A, that's in my range, and it has two preimages. It has Tim as a preimage, and it has Joe as a preimage. Is that okay? All right, so this means each element of the range has exactly one preimage. Because if it had 0 preimages, what would that mean? It wouldn't be in the range. It would still be in the codomain, but it wouldn't be in the range. If it had 2 preimages, well then you would have a situation where fx equals fy and x and y were the same. Or sorry, were different. Okay? Is that clear? Question? Yeah, so you could say each element of the codomain has at most one preimage. That would be the same thing. If it's the range, then it's exactly one, because if it were fewer, it would mean the range. Or you could say each element of the codomain has at most one preimage. So let's in fact write that down. That's exactly the same as each element of the codomain has at most one preimage. So you can think about it either way, whichever is more helpful to you is how you can remember it, but you should know that those two statements are exactly equivalent. Okay? So if you want to understand this in terms of the diagrams we looked at, the way you can do that is each element on the right has at most one incoming arrow. So in a diagram, each element of the codomain has at most one incoming arrow. If you want to understand it visually, that's how you understand it visually. So is the definition of injective okay? All right, so I promise that you will need to prove that a function is injective at some point. Yeah? If it doesn't have an arrow, so that doesn't tell you that it's not injective, right? Because it just says it can have at most one. So elements in the codomain, if they have 0 incoming arrows, that doesn't make it not injective. But it doesn't make it injective for sure. You need to look at all the rest. Other questions? All right, so let's think about how to prove a function is injective. So to show a function is injective, well, notice that there's two equivalent definitions because of the contrapositive. So really you can prove it directly or indirectly. The first way is to assume that fx equals fy and show that x equals y. That's one way to do it. So that would be directly. The second way to do it would be to assume that x does not equal y and show that fx does not equal fy. And that would basically be showing that it's true indirectly. All right? And the method you use depends on the function. Right? Some are easier to prove one way or the other way. I would recommend trying one first, because when that does work, it's usually relatively straightforward. All right? If you want to show that a function is not injective, then what you do is you give an x and a y such that x is not equal to y, but fx equals fy. So to show a function is not injective, what you do is you give an x and y such that x is different from y, but fx equals fy. And remember, that implication is universally quantified, so if you find a single exception, if you like, a single counterexample, then it's not true, which means that it's not injective. So these are your two choices when I ask you, is this function injective? You first decide whether or not you think that it is. If you think that it is, you should try one first, and then if that doesn't pan out, then two. If you think that it's not injective, then you should start looking for values x and y, such that x does not equal y, but fx equals fy. That's what you should be doing. So let's do some examples. So let's say we have a, b, c, and 1, 2, 3, 4, and the function takes a to 1, b to 2, and c to 4. So is this function injective? Okay, so the way you determine that is you look at every element. You look at element 1. How many incoming arrows? 1. Element 2. How many incoming arrows? 1. Element 3. How many incoming arrows? 0. Element 4. How many incoming arrows? 1. The largest number of incoming arrows I ever saw was 1. So that means that the function is injective. If at any point I had seen 2 or more incoming arrows, then it would not be injective. So this thing here is injective. As another example, if I have a, b, c, and the function 1, 2, 3, 4, and let's say a goes to 1, b goes to 1, c goes to 4, well, I look at 1 and it has 2 incoming arrows. 2 is bigger than 1, therefore it's not injective. Question? So if the cardinality of the left side, so let's say A, B, C, D, and the cardinality on the right side is less or more? Less? Okay, so let's say 1. Well, what I can do is I can say A goes to 1, B goes to 1, C goes to 1, D goes to 1. So it's, are you saying it's always not injective?
It's always not injective, right?
Oh, not injective, yeah. And the reason for that is everything on the left has to have at least one outgoing arrow, and there's fewer things on the right. This is an application of something called the pigeonhole principle, which you'll learn about in 2804. Yeah, so you can look at it that way for sure. That's a helpful fact to keep in mind, absolutely. Other questions? All right. So to be clear, if you do notice that situation, you should still give the x and the y, because we haven't proved the pigeonhole principle in class. All right. So let's move on to thinking about what happens when we're not given a graphical representation, but instead we're given some sort of formula. So let's say we have f takes the integers to the integers, and it's defined by f equals 3x plus 2. And I want to know, is that injective? So is f injective? What do we think? Is it injective or no? Yes. So why would you say yes? So what is 3x plus 2? It's a function, it's a line, it's a linear function. And if you imagine a drawing of a line, does it ever cross does it ever take on the same y value twice? No, unless it's a horizontal line, in which case it would have slope 0, but this doesn't have slope 0, this has slope 3. So intuitively we know this thing is probably going to be injective. So I would say to myself, okay, well let's try to prove that it's injective. So we go up to our list of what to do, and the first thing is, if we want to show it's injective, we should assume that fx equals fy and show that x equals y. So we assume that fx equals fy. Okay, well fx equals fy, that's the same thing as saying 3x plus 2 equals 3y plus 2. Right? That's exactly the same as that. I'm just subbing in the definition of the function. Okay, well, we can cancel the plus 2's on both sides to get 3x equals 3y. And we can cancel the 3's on both sides to get x equals y. So that means if I assume that fx equals fy, then I know for sure that x equals y. And that's the definition of injective. So in fact, our idea was right. Therefore, f is in fact injective. Now you might think that this trick works all the time, but you'd be wrong. So let's say we have a very similar function. Integers goes to integers, and it's f of x equals x squared. So is f injective? What do we think? No. So why not? So f is a quadratic equation, quadratic function, which means it looks like a parabola, which means that for a given y value, as long as it's above the bottom of the parabola, it'll hit the parabola twice. The parabola will hit that y value twice, and that y value is the output of the function. So intuitively, it doesn't seem like this thing is going to be injective, but let's say we weren't thinking too carefully and we forgot about that. So let's see what happens when we do the proof. So we assume that fx equals fy. Okay, well that's the same thing as x squared equals y squared. And the natural thing to do is to take the square root of both sides. So the square root of x squared equals the square root of y squared. And what you'd like to say is, oh, we have a square root, so we can infer that x equals y.
No.
Why is that wrong? Yep.
The square root of a number can be positive or negative. So that has to be plus or minus x equals plus or minus y.
Yeah, in fact, what we've inferred is this. Plus or minus x equals plus or minus y. So that's really the same as x equals plus or minus y. That is not the same thing as x equals y, as I hope everyone sees, right? 5 does not equal minus 5. So this is not right. But this isn't a proof. It just means maybe we weren't clever enough. This proof didn't work, but that doesn't mean for sure it's not injective. To show that it's not injective, you would want to show a value x and a value y that are different but give you the same output. So this doesn't seem to work. So we try to prove it's not injective. What values of x and y should I try? Yeah? 2 and minus 2, sure. So let's say x is 2, y is minus 2. Well then f of x equals x squared, which is 2 squared, which is 4. F of y is y squared, which is minus 2 squared, which is also 4. So notice that we have x does not equal y, but f of x equals f of y. So when you have these two situations, that means that f is not injective. So we found two counterexamples. And any x that equals minus y, as long as it's not 0, will do this job. So you could have picked 1 and minus 1, 3 and minus 3. Anything will work. Any questions about that? Yeah?
So, if you think 0 is against what's injective, what if there's a function that has a greater set of values like 0? If that means it's injective.
Yeah, so that can happen, absolutely. On tests, I will give you a function where it's fairly easy to find the exception. But in general, you're right. It could be quite big before you find the first time that this happens. And that's what makes it difficult sometimes. Sometimes trying the proof, like we did here, can give you a hint at what x and y might be, or at least sort of where they might be, if they're likely to be large or small. But again, you can't rely on that. Other questions? Yep.
I guess as soon as you find one value for x and y where this proves that it's not injective.
Right, you only need one exception to show that it's not injective because the definition was universally quantified. So we only need one exception to show that it's false. Other questions? All right, so let's move on to the next term, and that's the other one, surjective. So a function f from a to b is said to be surjective, and this is sometimes known as onto. So surjective goes with onto, injective goes with one-to-one. If for every output, so for every b in B, there exists an element A in A such that FA equals B. Okay? And if that's true, the function is a surjection. So really notice that this says there exists. So that means there's at least one value. So every output is mapped to by at least one value. Could be more, but it's at least one. So there's never any values that don't have incoming arrows. Every value has at least one incoming arrow. So every output value, I mean. Does that make sense? So it's surjective if every output value has at least one incoming arrow. So this means that every element of the codomain has a pre-image. So what's another way of saying that? Yeah?
If the range equals the codomain, then it's surjective.
Yeah. So saying it's surjective is the same as saying the range and the codomain are the same. Because if they're the same, then there's no output element that doesn't correspond to an input element. Right? We already know that the range is a subset of the codomain. If it turns out that if they're actually equal, then it means the function is surjective. That's another way of thinking about it. So equivalently, the codomain and the range are the same. Okay. So in a function diagram, in the diagrams we've been doing, it means that there is at least one incoming arrow to every element in the output set. All right, I find it helpful to think of these in terms of what's going on in the arrow diagram, but you can remember it however you like. Okay, so is it clear what the definition of surjective is? We're comfortable with what a surjection is? All right, so let's talk about how to show a function is surjective. To show a function is surjective, start with an arbitrary output element and show how to get it. So show what its pre-image is. So take an arbitrary b in B, and by arbitrary I mean you don't pick it, it's picked for you. It could be anything, right? This is exactly like what we did for our quantified or our rules of inference for quantifiers. So it's arbitrary, and show what a pre-image of B is. So it could just be one, but it could be more than one. So what that really means is find an A in A such that FA equals B. And if B is arbitrary, this means you could have done it for any B, which means that it's true for every B. This is exactly like universal generalization. Yeah? Yeah, essentially what you're doing is computing the inverse of a function. I'll talk more about what exactly inverse means later, but yeah, that's what this feels like doing, yeah. Other questions? Okay, so let's talk about how to show it's not. So to show a function is not surjective, all you have to do is give a B such that no input leads to B as an output. Give a B in B such that FA does not equal B for any A. Okay, that's the opposite of surjective. All right, so let's do some examples to see how this works. We'll start with the picture approach. So let's say we have A, B, C, D, and we have 1, 2, 3. And my function looks like this. Is this going to be surjective? Yes, because I look at everything on the right and I count the incoming arrows. 1 has 1, 2 has 2, 3 has 1. Every number I said was bigger than 0, therefore it's surjective. On the other hand, if I have A, B, C, D, and 1, 2, 3, what I could have is something like this. And in this case, is this going to be surjective? No, because 1 has 3, that's fine. 2 has 1, that's fine. 3 has none, therefore it's not surjective. Is that okay? All right, so let's try doing it with functions. So let's say we have a function f that goes from the integers to the integers, and it's defined by f of x equals x squared. Is that surjective? No, yes. So if you say no, why isn't it not? Or why is it not surjective?
If you know that from an example we've done before, that the range is the set of all non-negative perfect squares. 7 is not a non-negative perfect square. It's -4.
Right. So there's a couple of ways to see this. That's one of them. The easiest one I know is to look at a negative number, because this will never be negative, even if it is a perfect square. But you're right, all of the positive numbers that aren't perfect squares are equally valid examples to show that this is not surjective. So this is not surjective. And there's lots of ways to see it. One is there is no x such that x squared equals -1. Right? There's no such x because I require that my inputs are integers. So really there's no integer x such that that's true. There is the complex number I that makes that true, but it has to be an integer. Any questions there? So an equally good example on this would be, say, 3, because there's no integer x such that x squared equals 3. That's a perfectly good example that you can do as well. That's completely fine. I like to do the negative one because you don't even need to think, right? It's clear that when you square a number, it will be positive, so nothing will have a negative output, but this is perfectly valid as well. All right, what about this function? So f goes from the reals to the reals, and it's f of x equals 3x plus 2. Is that going to be surjective? Yeah, so why is it going to be surjective? Well, it's a line, right? And it has non-zero slope, which means eventually it's going to hit every possible output value. Right? Its slope is, is finite, so it will hit every possible output value. Okay, but that's just intuition. That's not a proof. This is surjective. But we need to prove it. So to do that, well, suppose we have some image that we want. What pre-image gives us that image? So suppose we have image y. What pre-image gives us that? So gives us y. So y is the image. What do images look like? Well, they look like 3x plus 2. right? No matter what you get out of this function, it has the form 3 times a number plus 2, right? It has to. That's the definition of the function. Okay, well, now we want to find out what do we have to plug into the function to give us that. What that is the value x, right? The value x is the pre-image we have to put in the function to give us the image y. So if we can solve this thing for x, then we're done. And in fact, that's not too hard. So that's exactly the same as y minus 2 equals 3x by bringing the 2 over. And now divide through by 3. So y minus 2 over 3 equals x. So if you want the answer y, subtract 2, divide by 3, and put that in the function. Does that make sense? Yeah?
Is it okay if you get some values that there must be 2 possible values for that?
So the important thing is that at least 1 maps to that. If you find that there's 2, that's okay. It won't be injective in that case, but that's still fine. All right? So that is the pre-image. So what this means is to get an output of y, give the input y minus 2 over 3. Is it important that f goes from the reals to the reals here?
Yes.
So what if it went from the integers to the integers? So if it went from the integers to the integers, is it going to be surjective even? So would I ever be able to get the answer 1? No, right? So I could put in minus 1, and it would give me minus 3 plus 2 is minus 1. The next one it would give me is 2. So I can't actually get 1 out of that if I insist on going from integers to integers. So this is another case where you have to be careful with what the function is doing. Yeah?
Can you change what kind of number you accept? Like, can you have something that goes from integers to reals?
Yeah, absolutely. That's fine. Yeah, you can definitely do that. And in that case, sometimes it's a little bit more subtle when you're doing these things. You need to make sure that you're considering the right sets. But for now, even if I change this from reals to integers, that affects whether or not it's surjective. In this case, it won't be surjective because some integers you don't get out of this function. And this kind of makes sense because if you look at the graph of this function, if it goes integers to integers, it's not a line, right? It's a bunch of points on a line, but it's not the entire line. So anything on that line that's an integer, but not one of those points, won't be the result of the function. All right. Any questions about this? All right. So one thing you might want to notice, and as an exercise, figure out why this falls apart if you try to do this kind of proof technique. It's the same thing as last time, really. All right. So notice that injective is the same as at most one image, and surjective is the same thing as at least one image. So if math has taught you anything, it will be that there is another property that happens when both of these things are true at the same time, and that will be when you have exactly one image for every pre-image. So if a function is both injective and surjective, then each element of the domain is mapped to a unique element of the codomain, which is the same as the range. And we call such functions bijective. Bi meaning two. They're both injective and surjective. They're both of those things. Okay, so a function that is injective and surjective is said to be bijective. And we call it a bijection. All right. So if you want to show that a function is a bijection, that it's bijective, you do two parts. You first show that it's injective, using the techniques we already saw, and then you show that it's surjective, using the techniques that we already saw. So if I ask you to do a proof that a function is bijective, I'm really asking you to prove two things. I'm asking you to prove that it's injective and surjective. All right, I'd like to do a few examples now, if I could. And these will illustrate something that's very important that you understand. So here's one function, a, b, c. And it goes to 1, 2, 3, 4. And it takes A to 3. It takes B to 4. And it takes C to 1. So is this function injective? Yes. Is this function surjective? No. Okay, here's another function. This takes A, B, C, D to 1, 2, 3. This one takes A to 2. It takes B to 1. It takes C to 3. And it takes D to 2. Is this function injective? No. Is this function surjective? Yes. All right, let's continue. This next function takes A, B, C, D to 1, 2, 3, 4, and A goes to 4. B goes to 1, C goes to 2, D goes to 3. Is this function injective? Yes. Is this function surjective? Yes. So what do I know about this function? It's a bijection. It's bijective. Another example would be A, B, C, D going to 1, 2, 3, 4. And here A goes to 1, B goes to 1, C goes to 4, D goes to 4. Is this function injective? No. Is this function surjective? No. So what do these four examples show you? Yeah?
So if there's a greater if the size of the set of the outputs is greater than the size of the set of the inputs, it can't be surjective. If the opposite is true, it can't be injective. And if they're both the same size, it's either bijective or not injective and not surjective.
Okay, so there are rules like that, for sure. And that's good. You would have to sit down and prove those individually. Yeah?
This shows us 4 different cases of the bijective.
Yeah, this shows you the 4 different ways 2 functions can be related, or 2 sets can be related by functions. Okay? So this tells you it's possible for a function to be neither injective nor surjective, down here. It's possible for a function to be injective and surjective. It's possible for a function to be injective but not surjective. And it's possible for a function to be surjective but not injective. So what you should take away from this is that it's never okay to just prove injective but not surjective if I ask you if it's a bijection. Right? Because all 4 possibilities can happen. You've seen them. They're right here. So it's never enough to stop. There's one more example I want to show you before we go, and that's this. If I have A, B, C going to 1, 2, 3, 4, and it looks like this. So A goes to 1, A goes to 3, B goes to 2, and C goes to 1. Is this injective? It's not a function. And I know it's not a function because A has 2 outgoing arrows. So if I ask you for a function diagram and you draw something that has 2 outgoing arrows, you have not given me a function, so you haven't answered the question. So just because you can draw it does not mean that it's a function diagram. If you want to model what you're doing in this way, that's fine. You just can't use a function. You use something else called a relation. All right. So what I'm going to do now is return your first assignment. I apologize in advance. They're in no particular order, and there's a huge number of you. For your next assignment, beside your name, write down which tutorial section you're in, and then we'll return them in the tutorials. But for now, this time, we won't be able to do that. All right. That's it for tonight.